Okay, so just like everything else we've looked at for gravity, we've looked at for electrostatics. We've done force of gravity connecting to electric force. We've done gravitational field strength connecting to electric field strength. And so that we looked at gravitational potential energy, we are also going to look at electrical potential energy. So recall that the force between two charges is not constant and varies with the distance. So we've got Fe equals kqq over r squared, just like gravity, which I'm going to add in here. Fg was gmm over r squared. So we also can recall that the work done can't be calculated for gravity using work equals Fd when we've got a force that varies with the distance. What we've got to do is we've got to find the area under an FD graph just like we did using, I give you an example using calculus. So the integral to sum up, and I told you didn't have to know it, and you just had to recognize it and see it, which is, what I showed you. And so we're going to just basically take that result and we're going to pull it up ahead. So the result that gave us was that the potential energy due to gravity is equal to negative gmm over r. And so the extension here is that the potential energy for the electric potential energy outside of a charged object is going to equal kqq over r. We're not using the negative, it's not negative, if there's a reason for that. With gravity, it was only attractive, and the math dictated that it would be negative. But for this particular, for electric potential energy, instead of having it being explicitly negative, what we're going to do now is for energy, we include the positive or negative on the charges for Q and little q. And just like before, we can see here that with that r in the bottom, as the distance gets greater and greater and greater, potential energy is going to get smaller and smaller and smaller. So just like for gravity, we have at infinity, the potential energy equals 0. So all of that is still very much true for this particular concept as well. So let's just jump into it. We want to find the potential energy of a 75 microcoulomb charge that is 3 centimeters from a 120 microcoulomb charge. And we want to write the work energy equation, and we want to find the work done by the applied force. So we're just going to go straight to the end. We want to know, so this was the original setup. We had them 0.03 centimeters apart. And afterwards, we've moved this guy out to infinity, infinitely far away, and we want to know how much work was done to make that happen. And so there has to be, these two are attracted to each other. There is an attraction here, one's positive, one's negative. So because there's an attraction there, to be able, or to pull the thing away, work has to be added to the system. So we're going to have our initial energy. We're just going to jump straight to doing C. Energy initial plus work equals energy final. We're back here again, except the type of energy now is different. We're using electric potential as opposed to gravitational. So if we look at what's at the beginning, there's potential energy here. So we're going to have potential energy initial plus work, and it's been moved to infinity. So I'm assuming we can assume at infinity it's no longer moving. So we're just looking at, so out at infinity, there is no potential energy, it's 0, and there's no kinetic energy. So the potential energy initial is kqq over r, which I think I got that right before, kqq over r, plus work equals 0. So we're going to have 9 times 10 to the 9. We're going to have 120 times 10 to the negative 6 positive, and we're going to have negative 75 times 10 to the negative 6. Plus work. That's going to be divided by, they're initially 0.03 meters apart, so 3 centimeters. It's equal to 0. We can see here this is negative. So when I add it over, it's going to become positive, and so we're going to get work equals, if you actually do this math, actually I'll leave it this way. If you calculate this, this is negative 2,700 plus W equals 0. So we add that over, and we get positive work. We had to add energy to the system to pull them apart. We get 2,700 joules. So by incorporating the signs on the charges, we're actually able to accurately reflect on whether work is being added to or taken out of the system. So by the relationship, we have like charges have positive potential energy, and this makes sense because it takes work to overcome the electric repulsion and push the charges together. You'll see what that means here in a sec. So we want to find the work required for some external agent to place a 2.5 millicoulomb charge now, 5 meters from a 1.75 millicoulomb charge, assuming that this one is originally an infinite distance away. So we set this thing up exactly the same way. We've got an initial energy plus work equals our final energy. Initially, this thing's infinitely far away, so there is no initial energy. So we have to do work to bring them together. So we've got a final position here, and again, they're not moving, so there's no kinetic energy. Now we're just going to have potential energy final. So work is going to equal KQQ over R, 9 times 10 to the 9. Charge is 1.75 times 10 to the negative 3, 2.5 times 10 to the negative 3, and we're dividing that by their 5 meters apart. We include the signs on the charge, again, with positive and positive, so it's going to take work to bring them together. So the work done to bring these two positive charges together is 7,875. They're repelling, so we have to do, so we have to do work to bring them together, and this shows that. Same thing, let's do it again, except we're looking at different kinds of, slightly different kind of situation. So in this particular situation, we've got a proton and an electron. So this guy's going to start at rest. And the difference here is that it doesn't take an external agent to make this happen. If the proton is fixed, the electron is going to be attracted to the proton because one's positive, one's negative. The important thing to recognize here is if that no external agent is pushing the charges around, then the energy of the system is going to be conserved. And what that means is work done is equal to 0. These things just do it themselves using the energies that they have available to them. So originally, this distance here is 2.5 times 10 to the negative 11 meters. It's released and moved towards the proton. We want to find the speed when it's this distance, 1 times 10 to the negative 11 meters. So here we're told that this thing's starting at rest, so Ke equals 0. We can see that. But there is going to be some potential energy. Here, kinetic energy is not 0. We are definitely going to have some kinetic energy. It's moving, and we're asked to find the velocity, and there's going to be potential energy here as well. Because there's no outside force, again, work equals 0. So let's go through and solve it. We've got energy initial plus work equals energy final. Work is 0. Energy initial is potential energy, just potential energy, and that's going to equal a potential energy final plus a kinetic energy. So potential energy, again, this is electric, not gravitational, so it's going to be K QQ over R equal R initial equals K QQ over R final. And we're going to add to that 1/2 mv squared. So we can start to fill this thing in. We have 9 times 10 to the 9. The proton and electron One is positive 1.6 times 10 to the negative 19. Again, these are elementary charges, and the other is negative 1.6 times 10 to the negative 19. And their initial distance is 2.5 times 10 to the negative 11 meters. That's going to be equal to 9 times 10 to the 9, 1.6 times 10 to the negative 19, negative 1.6 times 10 to the negative 19. And now they're ending 1 times 10 to the negative 11 meters apart. And we're going to add to that the kinetic energy of the electron. So it's going to be 1/2. The mass of an electron is 9.11 times 10 to the negative 31 times v squared. And it's that v, and it's that v that we're looking for there. This is just some number. This is just some number. Solve for each, subtract that over, multiply by 2, divide by this, square root, and you should see, and I'll leave that calculation to you just to verify, that the speed of the electron is 5.5 times 10 to the 6 meters per second. This thing is moving incredibly quickly, but that's the setup of the equation, of the question rather. Now, one last fantastic example, and we'll call it good. So, here we go. Here's the setup. In the diagram below, we've got a positive 1.5 microcoulomb charge, a positive 1.5 microcoulomb charge here, a negative 2.5 microcoulomb charge, and we want to find a whole bunch of stuff. We want to find the potential energy of the system, so how much energy has to go into creating this system. These two are going to be repelling, these two and these two are going to be attracting to each other. So there's going to be some attraction, some repulsion. How do we build this thing is the potential energy piece. We want to find the force and the direction of that force on this guy. And we want to find the electric field and the direction of the electric field here. And so we're combining everything that we've looked at so far in these last couple lessons. So for A, to find the potential energy, we're just adding up, we're finding all of the energies and we're adding them up. So find all potential energies for each pair and add them up. So we're going to have, I'm going to label these guys. I'm going to call this guy 1, call that guy 2, and I'm going to call this guy 3. So we want to find the potential energy required to put 1 and 2 together. I want to find the potential energy to put 1 and 3 together. So for this pair, and this pair. So potential energy for 2 and 3. And then we're going to add them all up. So this is KQQ over R, KQQ over R, KQQ over R. This is 9 times 10 to the 9. 1.5 times 10 to the negative 6. And I'm just, because they're both 1.5 times 10 to the negative 6, I'm just going to square it. And then the distance between them is 2 centimeters, so 0.02 meters. For 1 and 3, we have 9 times 10 to the 9, which is 1.5 times 10 to the negative 6, and negative 2.5 times 10 to the negative 6. And the distance from here to here, this is 2, this is 2. You have to find this distance. This is just going to be the square root of 2 squared plus 2 squared. So this distance here is actually 2.8 centimeters. It's going to be 0.028. And then I want the potential energy for 1 and 3. So that's just going to be 9 times 10 to the 9. It's going to be 1.5 times 10 to the negative 6. Negative 2.5 times 10 to the negative 6. And these guys are going to be 2 centimeters apart, 0.02. So that's all my calculation there. We can see all we have to do is add these things up. which I will leave to you, but I will tell you that the potential energy that I calculated was negative 1.88 joules. What that means is we actually have to hold these things from collapsing in on themselves. We're not holding them together and preventing them from blowing apart. We're actually kind of trying to keep them from collapsing in on themselves, is what this means. So that's part A. Let's take a look at part B. We want to find the force on this charge here, charge 1. For that, I'm going to use green. So we want to find F on 1. So we can see here what's going to end up happening here. We can draw it in here. These two are both positive, so this one's going to have a force upwards here. These two, one's positive, one's negative, so there's going to be a force inward here. So we have to figure out what those are and add them together. So we're going to find the force between 1 and 2. So that's given to us by KQQ over R squared. And that's going to equal 9 times 10 to the 9, 1.5 times 10 to the negative 6. Again, there's two of them with the same charge, so I'm just going to save some space and square it. And they are 0.02 meters apart squared. This value here is 50.625. I'm actually going to calculate these ones now because we don't add them together the same way. We have to add them like vectors, where these ones, energies just add normal. So these ones I'm actually going to calculate individually. So my force here, 1 and 3, it's going to be KQQ over R squared. So we've got 9 times 10 to the 9. We've got 1 is 1.5 times 10 to the negative 6. The other is 2.5 times 10 to the negative 6. Again, with forces, we do not include the positive and negative. We just use the positive and negative to give us the directions. And the distance we already calculated from the previous part, 0.028. Square that. If you do that, you'll see that the force between 1 and 3 is 43.048 newtons. And so I'm just going to redraw it here. We can see here that that first charge there, 1, has an upwards force here and a downwards force here. So this is F1 and 2. This is F1 and 3. So we've got to add these things together properly. And so when we're adding vectors, we add them tip to tail. So we're going to take this one here, and I'm going to slide the tail of him up to the tip of this guy. So what we're going to get is we're going to get a drawing that looks like this. I got a force going up that way, and I got a force going down this way. And we want to figure out what the resultant force is, and the resultant force goes from the tail of the first to the tip of the second. This guy is 50.625. This guy here is 43.048, and we have to have that angle there. Well, what's that angle? Let's go back and take a look at our original picture. This is a square. So this angle here is 45 degrees. When I take this and I slide it up here, this is vertical, this is an angle, or at the same angle this is at, and so that's going to be 45 degrees in there as well. So we just use cosine law. Cosine law is going to give us that this is 36.52 newtons, and then we have to use sine law to find this angle here. And we're going to find, so I'll call that theta, we're going to find that theta, our angle, is 56.5 degrees, say right of the vertical. So we're not given directions here, I'm just using that from the picture. We don't know how that thing's set up. That's the procedure for the force. And now let's go through and find the electric field. So I'm just going to go And we're going to do this part over here. I want to do that in blue. So here we want to go for electric field. So what we're going to have to do is we're going to have to find all the electric fields, and then we're going to have to add those up vector-like as well, because electric fields are vectors. They have a magnitude and they have a direction. So we can find the electric field from 1 is kq over r. So that's just going to be 9 times 10 to the 9, 1.5 times 10 to the negative 6 over, and then the distance from our first charge to the field point is 0.02 meters. Actually, and that's squared. That's squared. So we find out that E1 is 33,750,000 newtons per coulomb. And if we look up here, we can see if this is positive, the electric field is going this way. So that's E from 1. E from 2, kq over r squared. So that's going to be 9 times 10 to the 9. The charge is the same, but the distance is different. Now we want the distance from here to here. Well, it's a square, so that's just going to be 0.028 meters. Square that, and we find that E2 is 17,219,388 newtons per coulomb. And he's going up that way. There's E2. And then E3 is kq over r squared, and that's going to equal 9 times 10 to the 9. The charge down there is 2.5 times 10 to the negative 6. So just like forces, we don't use the positive or negative charge, we just use that for direction. The distance there is 0.02 squared. So E3 is going to be 56,250,000. If we take a look at what's going on here, this guy is going to be straight down. That's E3. So what we've got to do now is we've got to add these things together. I'm just going to redraw it down here so we can see it. We've got one going this way. This is 33,750,000. We've got one going this way. This is 45 degrees here. And this one is 17,219,388. And we've got one going straight down, 56,250,000 newtons per coulomb. And so we can see here, I'll put newtons per coulomb on all of them. We can see here that to add these three things together, we're going to have to use components. It won't give us a nice little triangle. It'll give us kind of a weird geometric shape to add all of these things together. So what we're going to have to do is we're going to have to break this one up into components. I've done that already. I'll leave you to do check my math. But we can see here, and because this is 45 degrees, these two components actually are going to be the same. So I found them to be 12,175,946, and this one's also 12,175,946. And so we can redraw this thing together. We're going to have these two added together, the 33 million and that 12 million. We're going to add those together, and it's going to give us one that looks like that. 45,925,946 newtons per coulomb. And then we're going to have this downward one subtracting, we're going to subtract this from this downward one. So it's still going to be downwards because that's 56 million. Up is only 12 million. So it's still going to be down. And it's going to be, what did I find that to be? 44 million. 74,000 and 54 newtons per coulomb. So to actually find the magnitude and direction of our electric field at that point up there, we have to add these two vectors together like we do. I'll leave you to do the math. I found that this angle was 43.8 degrees, and the net electric field I found to be 63,653,081 newtons per coulomb. And that's it. We've done A, B, and C. It's a fair bit there. And they're all disconnected, but at this point you can kind of see where everything is headed. So that's the last example out of this lesson. I want you to do a couple questions. I would like you to take a look at 1 to 3. I want you to take a look at number 5. I want you to do 7 as well. Comments, questions, concerns, feel free to join my office hours, and I will be happy to help you.